Good afternoon. My name is Nikhil and I am a student of University of Florida. This presentation is for the course Pattern Recognition. For the introduction, one way big retail stores improve customer experience is by dividing their visits into trip types. The goal of this project is to divide these visits with a more limited set of features which requires feature extraction and processed data, and the processed data is subjected to an SVM with RBF kernel. Doing so gives us an error rate. The overall error rate of our support vector machine with RBF kernel gave us 48%. So how shopping trip types influence purchases made on promotion and unplanned purchases is looked at. The problem statement is to characterize the trip types contained in this data, which is provided by Kaggle, into 38 distinct types. This is a multi-class classification problem with 77 extracted features. An SVM is the learning model used since it is a non-linear supervised learning method. SVM is the model used to train the data. So this project consists of data processing, feature extraction, model formulation, and finally training and testing. Firstly, let us consider data processing. So the raw data from the Excel sheet looks like this. So it has a trip type, visit number, the day of the week, a UPC number, a scan count which corresponds to whether an item has been bought or has been returned, a department description, and a fine line number. So to begin with, to process this data, we need to convert all the character values into numerical values. Hence, let us consider weekday and department description. For weekday, I have decided to number them 1 to 7 depending on the day of the week. Similarly, the department description is numbered from 1 to 70 according to the table, according to the appearance in the provided datasheet. It is found that 3% of the data set was missing. I decided to ignore all the missing data. Next step in the process is the feature extraction. Fine line number and UPC number have been ignored due to its large number. A feature is extracted where for each different visit number, the corresponding department description and weekday is checked. The total number of product bought from each department is counted. A positive value is assigned for a product bought, and a negative value is assigned for a product which is returned. These positive and negative values are fed into scan count. So here is a graph of the data which has been processed. Since we have decided to ignore UPC and fine line number, I have blackened these two columns. From the pre-processed data, 77 features are extracted. Department number is the first 70 and the next 7 are the weekday numbers. The total count of products each department sells is recorded in the 70-dimensional department feature, and which day of the week is recorded in the 7-dimensional weekday feature. Hence, this table transforms into a table which is a matrix of 94247 cross 77. Here the here we have 70 columns of departments, 7 columns of weekday, and a class label column. Next step is the model formulation. After feature extraction, the dataset obtained can be represented as this formula right here. Y output can be predicted for any given input. So the probability that any given input belongs to each class C is obtained using formula 3. So now we need to set up our feature extracted dataset for the purpose of training. Since we obtained 94,247 samples from the feature extraction process, it is split up into two sets, the training set and the testing set. The training set contains 70,000 samples, whereas the remaining samples, which is 24,247 samples, is given to the testing set. There are two ways to sample the data. One is random sampling and the other is proportional sampling. In random sampling, 7,000 random samples are assigned to the training set and the rest is assigned to the testing set, whereas in proportional sampling, a ratio between number of samples in each class to the total number of samples is kept while splitting the processed data set. Hence, we obtain 69,998 samples for the training set and 24,266 samples for the testing set. Now we come to the training. SVM with RBF kernel is a method used to train the data and generate a model. We already know that it is a nonlinear supervised learning method. The kernel is used to map data, which in the input space is not separable, onto a higher dimensional feature space, where separation becomes easier. The RBF kernel is given by the following formula. Our goal is to minimize the error rate, which is done by using formula 11. Optimized value for associated parameters are needed for kernels. Grid search is used to find the tuned and optimized values of gamma and C parameters. SimFit, SVM fit is used to train 70,000 samples, and the gamma parameter and the C parameter is given to SimFit. The software package PMTK3 is used to train SVM, which is a pattern recognition package. Now for the results. The overall test error obtained was found to be 48% for proportionally sampled data. Class-wise error was also found using the following formula, where the error is the number of misclassifications divided by the total number in terms of samples. This figure is a plot of class-wise error when SVM model is trained with random sampling. When the system is trained with proportional sampling and random sampling, this is the plot which is obtained. It shows the class-wise error of each class. As you can see from the plot, for most classes, the error for training with proportionally sampled data is lower than that of training with randomly sampled data. The reason being, in proportional sampling, data points from each class are chosen for training set as well as the testing set. This makes sure that both the sets contain a certain number of data points from every class. Whereas, in random sampling, it is possible that some classes may not be chosen at all in one of the sets due to its less occurrence. This leads to a high out-of-sample error if such classes are included in the training process. To show that classes are not uniformly distributed, a new graph is plotted, which shows the percentage of each class in the complete dataset. In order to get a better model, a large number of samples is required. To confirm this, the points marked in this graph are chosen. These points correspond to the classes with the lowest samples, that is, the least number of data points. When the error rate is checked for these inputs in the class-wise error plot shown in this diagram, it can be seen that they yield a high error rate. Hence, error rate is inversely proportional to the number of samples. Now, since the training process requires close to 8 to 9 hours, I have already run a couple of codes and obtained the errors. Here is a plot. Here is a plot indicating the error rate using SVM model as against error rate using proportionally assigned model. This brings us to the conclusion. Feature extraction, sparse features and high dimensionality of the feature space were the challenges of this project, which as shown before has been overcome. An overall error rate of 48% was obtained using proportionally sampled data, and error rate is inversely proportional to the number of samples as the last two graphs suggested. Proportional sampling is better than random sampling, that is, better class-wise error, as the class-wise error plots showed. Here is a list of references that I looked up, and this brings us to the end of our presentation. Thank you.